There are specific ways that we're going to move electrons using curved arrows in order to show how resonance structures can be formed, okay? So when we're moving electrons, we're going to use electrons in pi bonds or in lone pairs, like exclusively. Okay, so I'm trying to highlight this. Sorry about that. It took a minute. If you break a single bond, you break the compound. We can't do that. Third row and above can sometimes be what's known as hypervalent. What that means is that it can have more than 8 electrons, but we're rarely going to see that, especially not in this first semester of organic chemistry. So let's stick to the 8 electrons. Now, with the exception that there's 2 electrons for hydrogen. If we want to get picky, there's 6 electrons for boron most of the time, but we're not going to see that very much either. You can have carbon with a positive charge like we talked about in the last video. So it can have less than 8 electrons if you're going in that order, okay? But we're going to see how in a minute it's better to have 8 electrons around stuff when you can. Curved arrows begin where electrons reside and point to where they move. So like if you were to show that you moved houses, it would be your current house and you're moving to your new house. Okay, that's how that goes. That's a W. There we go. So you can only move electrons next door, at least for now. There's more complex stuff that we can get to later, but let's stick with, for now, that we need to move electrons kind of next door, okay? We don't move too far because that's just too much. So here's what I mean by that. So you can take this example here. We've got right there, okay? Notice that we're using this curved arrow to show that the electrons that are in the double bond can go from between those 2 carbons to between the 2 carbons over here. And so that's where that double bond would move. Now, we are not showing where the positive charge moves. The positive charge, where it is located, is a result of where the electrons live. We show movement of electrons, not of positive things. So realize that. Because what's on the outside of atoms is electrons. What bonds things is electrons. That's where the fun's at. Everything else is a result of those electron movements. Okay? So what we could have here in the second one is that we can move 2 things at once. And I kind of think of this sometimes as like windshield wipers. Because remember, you can't have more than 4 bonds on a carbon. And right now, this carbon in the center already has 4 bonds. So what we do is we're going to remove 2 electrons from this guy, but in order to do that, I need to move this double bond up so that the electrons go up to that other oxygen. Now what that effectively means is that the negative charge goes from one thing to the next. So resonance structures are only available in a limited set of criteria. You can't always move things around. So for example, here we have an oxygen that has a negative charge to it. And you could say, wait, I want to move those electrons down. You can't. Because remember, this carbon already has 3 other bonds. It can't take a 5th bond. So nope, that won't work. You got to have some place to move electrons out to. So some common patterns that you should be able to sort of see as we continue through resonance structures and examples. We have to be able to recognize what's next door. So vinylic positions, so things that are actually in the carbon-carbon double bond. So this carbon right here and this carbon right here. You can't have a charge there. However, if you have an allylic position, so things that are over here that are next door to a double bond, well, those can be stabilized through resonance. They can share with these resonance types of situations, okay? And so I showed some examples here. We could have a double bond with an oxygen with a negative charge next to it. So then we just move our electrons. Now, when you're moving electrons, you need to either move like a lone pair to the bond that's next to it. So that's what we're doing here. Or, and then in this case, we're taking a double bond and moving it to that particular carbon. Or like we were saying earlier, excuse me, you can have a double bond that is moving to a double bond right there, which is, actually one bond moving to the next bond over. That's a positive charge there that I'm trying to show. So you can go either from like lone pairs to bond to lone pairs, like that are right next door, or you can move the bond to the bond next door. Okay, so here's some other examples of sort of moving those things that I'll let you take a look at right there. Okay. When you have an sp3 carbon in the middle, that carbon will block any type of resonating possibilities, I should say. Because we can't take these electrons and move that down, because remember, there's 2 hydrogen here. He's already got 4 bonds, so he's totally maxed out. You can't take anything else and put that in there, okay? Same thing here. If you have a nitrogen with 4 bonds, we can't do anything else here. But if we have a nitrogen with a double bond, like you see down here, we can potentially move electrons onto that nitrogen. Now, it's rare to see a nitrogen with a negative charge, but it is a possible resonance structure. Okay. Pi bonds or lone pairs, allylic 2 carbocations will resonate. So we can have more than one resonance structure, just like we see here. So we have a positive charge here with a double bond right next door, so those guys can move over. And when they do, the positive charge is going to change as a result. And then the electrons move over again, and again your positive charge changes as a result. We don't move positive charges. The positive charge is a result of the electrons moving. Okay, so we don't show where electrons are moving, or where protons are moving, we just show where electrons are moving. So another way to represent this, like if you have nitrogen, we can take those lone pairs and move that into that bond right there. That will change where the positive charge is as well, but that's another example. Sometimes electronegativity is going to lead as to where you're going to find those charges. So if we take this double bond that is here and move those electrons up to that oxygen, this will make sense because we have an electronegative atom with a negative charge to it and a positive charge on that carbon. Even though these are not equal contributors to the resonance hybrid, excuse me, because you would favor the one without the charge, it does mean that this oxygen is going to be more partially negative than it would otherwise, okay? So let's look at some other types of things that we can talk about with resonance structures and how to determine which resonance structure might be closer to reality. So we would say that that contributes more to the overall resonance hybrid. Here, in order, here's how to tell which structures are most important. Number 1, look for the structures with the most filled octets. So we're talking about having an octet around oxygen, having an octet around carbon, the simple stuff that we've been doing with Lewis structures for a while. And I'm not talking about hydrogen, I'm not talking about the exceptions to the octet, and we're talking about just in general what you would have as an octet. Point number 2, the fewest charges is the one that's most favored. So if you have something that has 3 different atoms there and they've got charges on them, usually that's not going to happen. Remember, we want stable, and stable usually means the least amount of charge possible. So that's what we have to work towards. It doesn't mean that there aren't resonance structures with charges to them. It means that the overall hybrid will not look as much like one with lots of charges on it, okay? You certainly do not have something with a positive or negative 2 or positive or negative 3 very often at all with any significant contribution to the overall hybrid. Point number 3, when a formal charge is present, it's most often associated with an electronegative atom. So it's much more common to see a negative charge on an oxygen than a carbon, for example. Okay. And then sometimes we have symmetrical compounds that have about the same contribution to a hybrid. So like a carboxylate has a COO minus. And so those two things would sort of look in reality like an O and an O with a negative charge sort of equally distributed between those two oxygens and, through the carbon. So use those to guide and understand the resonance hybrid, but you still need to write out the resonance structures, and that takes practice, lots of practice. So definitely need to do lots of homework in this area, okay? Good luck. Thanks.